Okay, let's begin. So at the end of last lecture we asked this question. So given a set of propositional formulas capital S and a single propositional formula T, does there exist a purely syntactic way, which means a way which can be taught to a machine to determine whether T is a logical consequence of S? And one of the possible answers to that question is given by Hilbert style deductive calculus. So what is calculus? Calculus is a set of rules and some axioms. As you all may recall, axioms are those statements which we do not question, right? And in this case, these axiom schemata, I am using the word schemata because there are different schemes and they themselves have variables in them. So the important thing here is that you have to verify once I start writing down these axiom schemes. You have to remember that these are all tautologies. Remember or verify yourself, and I think nobody will have any objections in accepting tautologies as axioms because they are always true, so why not? And the rule of inference, there will be only one. So what is that? Modus ponens, or for short we are going to call it MP. Okay, so we will have this, and in order to do this properly we are going to use a slightly different adequate set of connectives. So when we defined propositional language and then propositional formulas SL, then we only used two symbols. What were they? Negation and conjunction. But just a moment. So आज नहीं कल लाइए प्लीज. हाँ, कल 12 बजे. कल सैटरडे है तो इसीलिए ट्यूटोरियल कल होगा. थैंक यू. Okay, so now today onwards we are going to use a slightly modified set of adequate set of connectives which uses negation and implication. Obviously there is no difference, implication and negation are adequate, you can check that. What do you need to do? As soon as you can express conjunction using implication and negation, you are done. Because we already know that conjunction and negation, they are together adequate. So how do you express conjunction using implication and negation?
Negation of P implies negation.
Okay, if you say so, I am going to believe that. Negation of P implies negation Q is same as, using De Morgan, it will be same as P conjunction Q. Okay, so any questions about this? This is the way we are going to do it. There is another answer to this question, that is natural deduction system or Gentzen style system. But we are not going to cover that in our course. If you are interested, please go and read about it in any good logic book. I have given you lots of references. Okay, that has very few axioms, but mostly it contains rules of inference. Okay, so what are these axioms? So we are going to call them logical axioms. And short form is LA. So these logical axioms, there is 4 of them. LA1 is the statement S implies T implies S. Can you check quickly? If you take this statement, S and T are any formulas, then can you check that this is a tautology? If S is false, then false implies anything is true. If S is true, then anything implies true is true. So therefore the second part will be like T implies S will be true. So this is actually a tautology. Yeah, so I should here I should write for all S and T in SL, this is LA1, logical axiom 1, but it is not a single axiom. Please notice, it is lot of axioms put together, because there is one axiom for each S and T, for each pair S and T, right? So there are infinitely many axioms here. That's why we are calling it axiom schemata. It's a scheme. Yeah, S and T are variables. They are not propositional variables. They are formulas. Any arbitrary formula can be put in there, and then still it will give us a logical axiom. Because as you already confirmed that this is a tautology, no matter what S and T are, it's going to remain a tautology. Okay, so this is an axiom scheme, not just a single axiom. I did not write propositional variables for S and T. I said any arbitrary formulas S and T, this one is a logical axiom. Okay, this is called, I'm going to write their names, although you don't need to remember them at all. This is called law of affirmation of consequent. Okay, so affirmation of consequent. Consequent is S. T is arbitrary, and in general, in formal proofs, this particular axiom is very useful because it allows you to talk about any, introduce any arbitrary T. Okay.
Sir,
yes?
can we only use L instead of SL?
If you only use L, then your proof system won't be strong enough. Yeah, so that's why you need the strength of all of them. I'm going to write one extra thing, but that's okay. So I should add a U also here. Yeah, ST and U for all ST and U. The second one is something which you can already see what's happening. What does it look like? Right. So let me write its name. It's called self-distributive law of implication. Okay, so S implies T implies U implies S implies T implies S implies U. So S, T and U are arbitrary. Okay, so LA3, now LA3 is very simple. This is called double negation elimination. Name is simple, double negation elimination. And finally we have LA4, that is, now you tell me what it looks like. Contrapositive, yes, law of contraposition. Okay, so if you know the contrapositive of a statement, then you know the statement. Now here I am going to give you an exercise. Verify that all logical axioms are tautologies. Yeah, just so that you can confirm this. Well, okay. Now, the only rule is modus ponens. But how to use these things? Yeah. Once we have these ingredients, how to use them? So there are actually, we are going to use induction to construct a proof, a formal proof. Yeah. And in that induction there will be two basic steps. First one is, base cases. Yeah. First one is a logical axiom. The second one is a non-logical axiom. And the only inductive step is this so-called rule of inference, modus ponens. I am going to write all these things down. So using this we are going to define a sequent. So there is a bunch of terms, but once I start writing an example of a formal proof, all these things will be clear. So let me go to the next slide and start talking about it. So, just before we proceed, modus ponens. Yeah, so this is a rule of inference. So for S and T in SL, here I am going to be a bit sloppy. If we have S implies T and T, then we have T. Oh, sorry. Yes. Here I am supposed to write S. If we have S implies T and S, then we have T. Now, I am being sloppy in which word here? We have. Yeah, what does that really mean? So I am going to make that precise by defining a sequent. Okay, given S subset of SL and S and T in SL, say that now notice, T is a deductive consequence of S. So read, T is a deductive consequence of S if one of the following is true. Okay, so now there are two base cases. The first one is LA. Okay, if T is a logical axiom, then T is a deductive consequence of S. See, logical axiom means a tautology, and tautology in the Boolean algebra, where does it sit? At the top. So deductive consequence, also think of it as less equal. So anything implies top element, implies or less equal top element, right? It's the top element after all. So therefore logical axiom is simple to deduce. You are deducing a tautology, so no problem. Then the second one is non-logical axiom. NLA is a non-logical axiom. So if T belongs to S, then T is a consequence, deductive consequence of S. So basically this is a single turnstile symbol. Whatever happens on the left, we should affirm that. Whatever we assume, we should affirm it. You understand? Yeah, I'm trying to find out all the consequences of capital S. So in particular, everything in capital S is also a consequence. But it is not because of some logic. That's why it's called non-logical axiom. It's because of my own assumption. Right? So non-logical axiom. And third one is of course MP. If we already have sequence S deduces S and S deduces S implies T, then we have this. So this is modus ponens, and you have to use this rule on two previous lines. You should have two previous lines, one which says little s is a consequence and another one which says S implies T is a consequence. Then you can conclude that T is a consequence of capital S. Is this clear? Okay, now the most important definition. A proof or a formal proof, yeah, more precisely, is a finite set of finite list, maybe I should use the word list, of sequence. Now, yeah, let's come to our senses properly. If we are thinking about any proof, do you go on and on and on? You finish after a finite amount of time. Every single statement that you make in mathematics that either follows from the hypothesis, which is a non-logical axiom, or something which is a logical axiom, it's always true. It was proved elsewhere, or it is always true because we have like it's part of our mathematical axioms, or it was deduced from two previous sentences. We combine two previous arguments to give a new argument. That's how every single mathematical proof is written. Of course, in reality, the rules of inference could change. Yeah, it might become more complicated. Our ordinary mathematical proofs are much more complicated. As I already mentioned, we are studying propositional logic, so this is the baby version of logic. But you can understand the idea. Every formal proof has finite length. I mean, it could be 100 pages, but 100 pages is still finite. We cannot go on and on. Right? Whatever rules we have. So for example, induction we assume. So we can write proof using induction. But for any argument, we either rely on our hypothesis or something that cannot be questioned. And we deduce new things from existing things. Right? So even let's recall Cantor's theorem. We start with some set and then we argue about that set, that if this happens, then that happens. If this happens, then that happens, and then we conclude something using contradiction over there. But this if and then, all these things in a very crude sense, they are one of these three. Either it's a rule of inference, or it's a hypothesis, or it's an axiom. Okay, so for the first time you are looking at the definition of a proof. Okay, now just saying this is not enough. I have to give you an example. So let us do an example of a formal proof. Okay, so suppose L is equal to PQR. Writing down formal proofs is notoriously hard in this particular Hilbert style calculus. Okay, because you have to use your imagination how to introduce new variables. Yeah, I will show you with an example, but proving completeness theorem is very easy with Hilbert style system. That's why I have chosen this over natural deduction. Okay, so suppose L is equal to PQR, and we will show this. If P implies Q and Q implies R are given, then what would you like to show? P implies R. Very good. So whenever we are writing down a formal proof of this statement, this sequent, then it should be a finite list of sequents such that the last sequent is precisely this. That is the meaning of writing a formal proof. And we are going to label number each line of the proof. Okay, so let's write down the first line. What can you say if you are given P implies Q and Q implies R? What can you conclude from there? P implies Q, not both simultaneously. Yes, we have to be very slow. Second one, I am not going to write this side, I am just going to put ditto. Yeah, I have to write a reason. Yeah, I cannot proceed without reason. So this is a non-logical axiom. Because I assumed it, I concluded it. The second one is of course going to be okay. What would be the third one? I still cannot use anything like modus ponens because I don't have the right setup, and I have already exhausted all NLAs. So now I have to rely on logical axioms. Now let me quickly take you back. Which logical axiom do you think could be useful here? Second one. And tell me what are S, T and U? P, Q and? If I use P implies Q implies R implies P implies Q implies P implies R, okay fine. I am just going to write down because she said so. Okay. So P implies Q implies R implies, well, for some time don't write it. Yeah, let's experiment and then we will, after finalizing, we will write it. I mean, this seems okay. Yeah, because ultimately we are going to get P implies R. And we will need two applications of modus ponens. Can you see that? First application to get rid of this part, and the second application to get rid of this part. Okay, now this part can be gotten rid of because we already have line 1. But how to get rid of this part? We have to use line 2 somehow. So let me first write down, this is LA2. So we have to get rid, we have to use this to obtain the first part of line 3. Any ideas? I am going to go back here. I already told you the first one is the magic one. It introduces new things without any problem. So what if I choose S to be Q implies R and P to be T? Then I will get it. Can you see? Now this is something which you have to do yourself. So Q implies R implies P implies Q implies R. If I write this is LA1, then I am done. I mean, now I can see the entire proof. Any questions why we chose this? Okay, now you can start writing again. So now the rest of the proof is fairly straightforward. I have to first conclude P implies Q implies R, and this is by using modus ponens on previous two lines. Which two lines?
4 and 2.
2 and 4. So we write MP24. Do not write any single line without number and justification. Okay, 6th one. So once we have P implies Q implies R, what can you conclude? See, this part is same as the first part of line 3. So I should use modus ponens. So I should say P implies Q implies P implies R, and I am going to use MP 35. And then finally I am going to use modus ponens again on line number 1 and 6. Okay, so we have concluded what we wanted, and this is a proof. It's a 7-line proof. Okay, those who like to solve puzzles, this is the best way to solve puzzles. Yeah, I mean, finding out formal proofs of statements which are obviously true, it's notoriously hard, believe me. Okay, any questions about this? Yes. Less than 7 lines, only 3 lines, only 2 lines, I have no idea. I mean, this is the shortest proof that I can come up with. So I don't want to say anything about the length. As long as the length is finite, you are okay. And there could be different proofs. Yeah, there could be multiple proofs of the same statement. Okay. Now I am going to write down some lemmas. Yeah. And those lemmas will have numbers because we are going to refer to them later in the proof of completeness theorem. So the first lemma is your tutorial problem. Okay, so I am going to write lemma 1, and it simply says this. There is a proof of S implies S. S implies S, is that a tautology? So now notice something. It's a tautology, so you want to derive a tautology from the given tautologies, because there are no NLAs. The left hand side is empty, so no NLAs. Only use logical axioms, means only use tautologies from the given set of tautologies to conclude other tautologies. So that's why this is called, I mean, this is also not an easy task. Yeah, try this out before tomorrow. Tomorrow we'll see the solution anyway, but try it out yourself. This is possibly the simplest looking statement, but the proof is not easy. Okay. Another thing, yeah. So finite character of proof lemma. Okay, so what, oh, by the way, I think this is a right time to talk about something, some question that's always in students' minds, but nobody answers it properly. What is the difference between a theorem, a lemma, and a proposition and a corollary? Okay, so if you are writing a book, a paper, if you are studying for a course, then theorem is a statement which you should never forget. It has independent value. Okay, now this is not, I am not giving you any mathematical explanation. I am telling you how things normally work in the mathematical community. Theorems are statements which you should never forget. Can you tell me any theorem from calculus course which you should always remember? Fundamental theorem of calculus. Yeah, it's a theorem. You should never forget that. Then Rolle's theorem, mean value theorem. Usually they also have some names. Now here we are going to write down several lemmas. So lemma, the plural of lemma is lemmata. So I mean, in practice this is the Greek plural, Latin plural, but we also use lemmas. So lemmas are important steps, they are key steps in the proofs of theorems, but they are of independent interest. They use lot of notation, so they are usually only of interest for writing the proof of a theorem. So they are tools developed on the way. So normally you call an argument a lemma, you separate it out from the main proof if it is used at least twice. Yeah, or it is of independent interest. And propositions are those statements which are small results but they are independent. Okay, so if you want to give something, like suppose you end up writing a paper, then usually the important results will be called theorems. While you are proving theorems, you are giving some definitions, and after those definitions you want to prove some consequences, some simple things about the new terms you have developed. Those will be propositions. And lemmas are techniques or tools that you develop on the way in order to prove theorems. Corollaries are consequences. Yeah, so if there is a statement of a theorem or a proposition or a lemma, and then a simple consequence of that statement, I mean, simple doesn't really mean the proof is very short always. It could be long, but the essential ingredient is that statement, the earlier statement in that proof. Then it is called a corollary. There is also some word which has been forgotten. It's called a scholium. 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 So scholiums are usually consequences of proofs. So basically it's a corollary of the proof of the above statement. Yeah, it doesn't follow from the statement alone, it follows from the proof of the statement. People generally don't use it, but yeah, one of my good friends and professors, he taught me about this, that scholiums used to be a thing in the past. Okay, let's come back here. So now I'm going to state this finite character of proof lemma. So it says that if S is a subset of SL and T is in SL, then there is a finite set S naught contained inside S such that S naught proves T. Can you tell me a proof of this statement? Finite character of proof. So capital S could be potentially infinite, and if T is a consequence of capital S, then actually T is a consequence of a finite subset of capital S. Why is that the case?
Because the proofs are finite.
Proofs are finite, yes. Next statement. Length of a proof is finite, obviously. So therefore, how many NLAs can you use? So done. You only choose those elements of capital S which are used as NLAs. The rest of them are irrelevant. Right? So I am not writing a proof. Finite character of proof. Yeah, I mean it only follows from a finite set of assumptions. You don't need infinitely many of them. Okay. Let's do the next thing. So monotonicity. Okay. Here we are talking about the set of consequences of a given set of propositional formulas. So capital S is given. Okay. Then there is a bunch of consequences of capital S. I am going to use this notation. Yeah. Suppose S is a subset of S prime and S prime is a subset of SL, and T is in SL. If there is a proof of T from S, then there is a proof of T from S prime. Why is it called monotonicity? Yeah, maybe I should explain that. So, in other words, if these angular brackets denote the collection of all the things which can be proved from T, then S subset of S prime implies that the angular bracket of S is is contained inside angular bracket of S prime. This angular bracket, this is called the deductive closure of S. Okay, why deductive closure? Can you tell me what is the relationship between S and its deductive closure? It's the filter generated by, but S itself is contained inside deductive closure. Yes? Why? Loudly. NLA, yes, NLA, right? So every single formula in capital S is a non-logical axiom, so you have a one-line proof of that. So therefore, S is certainly contained inside its deductive closure. And monotonicity says that if S is contained inside S prime, then deductive closure of S is also contained inside deductive closure of S prime. By the way, this filter idea, yeah, that hasn't been shown yet. You are, when you say that this is precisely the filter generated by capital S, you are using the logical equivalence classes of S, which is a totally semantic notion. Here we are still talking about purely syntactic notion. So once we prove completeness theorem, then this thing will be same as the other monotonicity, or this will be the filter generated by the logical equivalence classes of formulas in capital S. Yeah, so right now this doesn't mean anything. It's simply the set of formulas which have a proof from capital S. So completeness theorem will say that single turnstile and double turnstile are exactly the same. Yeah. So in fact we started it here. Yeah, lemma 1 is the first lemma which we'll need for the proof of the completeness theorem. Then finite character is also something very useful. Monotonicity, which we'll need. Yeah, so all these things we are going to write. Okay. You are supposed to write the proof of this, yeah, monotonicity for a tutorial, and I will give you the hint. It's induction on the line number of the proof. Okay, perhaps tomorrow also I will only say that. Okay, now we will start with the proof of a next important result, and that's why I am calling it a theorem. It's called deduction theorem. So suppose we have already seen the semantic version of this. Yeah, suppose S is a subset of SL. S and T are elements of SL. Then there is a proof of S implies T from capital S if and only if there is a proof of T from S union capital S. Capital S union singleton small s. We have seen the double turnstile version of this. Yeah, I mean you are simply transferring this S back and forth, and that is allowed. But the semantic version has a very simple proof. The syntactic version, we are supposed to do a lot of work here. Okay, so I will finish proving one side today, and next thing we'll do next week. Okay, so we suppose we have a proof. We have a proof of S implies T from capital S. Then I just want to increase the size of the left hand side. What is the way to do that? Loudly? No, not LA1. Just look here. It's here. Monotonicity. You want to add more hypothesis. Yeah, so that is allowed. So start with a proof. And use monotonicity to replace the LHS of each line by S union singleton S. Any problem here? I'm just adding one more hypothesis, little s. Okay, to obtain a proof of capital S union singleton small s proves S implies T. Now, how do I obtain? What do I want? I want a proof of S union singleton S proves T. How do I obtain it from here? I have this. Modus ponens on what? I don't have two statements yet. We can use NLA, right? So add two lines. What is the first line? S union and then done. So one side is quite simple. Yeah, so this side of the proof is done now. So we obtained the proof of just T from this. Okay, the other side is what is more complicated. Okay, so suppose I am going to start it today. S union singleton S proves T. So the idea here is that now you have a proof, a finite proof. We are again going to use induction on the line, and we are going to replace each line by finitely many lines. Okay, we will replace each line by finitely many other lines, so that in total I will again have a finite union of finite set of lines, which means a finite proof. Yeah, that is important. I always need a finite proof, but our idea would be that we don't want S union singleton S on the left hand side. We always need just capital S on the left hand side. Okay, so let me write down. So we replace each line of the proof by finitely many lines with S in the LHS and use induction. Okay, how many cases would there be? What are the two base cases of this? First thing would be, there are two base cases, LA and NLA, and then the inductive case is MP. Okay, so let us do that. So base case 1, okay, so that is LA. Suppose line number I is the sequent. Every line is a sequent. Yeah, I mean I'm using this. Then replace it with was there anything to be done here? Because logical axiom is a consequence of anything. Yeah, that's our original idea. So therefore there was nothing to be done. Sorry, there is something to be done. See, what we need is this. So we have to replace it with an appropriate line. So let me just take 2 more minutes. So okay, this is my LA1. So Ti was itself a logical axiom, and that was a consequence of S union singleton S. Now I am using LA1 for this, and using LA1 now I can conclude this MP on the above 2 lines. So I replaced this particular sequent, this underlined sequent, by 3 lines. I had little s on the left hand side and I pushed it to the right hand side. That's how we are going to do it with remaining base cases and inductive case. Okay, so let us stop for today.